You send a message. A lock icon appears in the browser bar. Your words travel across the internet as scrambled noise, and only the recipient can turn them back into plain text. That lock is not magic. It is a chain of mathematical operations running in milliseconds, designed so that reading your data without the key is computationally impossible at human timescales. Most people picture encryption as hiding a file behind one password. That is closer to access control than cryptography. Real encryption transforms the data itself. Every character becomes a different character according to a key and an algorithm. Without the correct key, the scrambled output looks like random noise. With the wrong key, decryption produces garbage. The protection lives in the math, not in a login screen. Encryption starts with plaintext, readable data. An algorithm and a key produce ciphertext, unreadable output. Decryption reverses the process with the same or a paired key. Modern systems use ciphers like AES, which operate on fixed-size blocks and repeat rounds of substitution and mixing. Change one bit of plaintext, and the ciphertext changes unpredictably. That avalanche effect is what makes pattern guessing useless. Symmetric encryption uses one shared secret key. Both sender and receiver run the same algorithm with the same key. One direction scrambles, the other unscrambles. AES 256 is the workhorse here, fast enough to encrypt gigabytes of traffic in real time. The problem is distribution. If you and a stranger need to talk securely, how do you share the key without someone intercepting it first? Sending the key over the same network you are trying to secure creates a chicken and egg problem. An eavesdropper who captures the key can decrypt everything that follows. Early internet protocols solved this by meeting in person or using couriers. That does not scale to billions of daily connections. The breakthrough was asymmetric encryption, a system where the key used to lock and the key used to unlock are different. Asymmetric encryption uses a key pair. The public key can be shared openly. Anyone can use it to encrypt a message, but only the holder of the private key can decrypt it. RSA and elliptic curve algorithms make this practical. You publish your public key like a mailbox slot. Anyone can drop a locked package in. Only you have the private key to open it. The private key never travels. HTTPS uses both approaches. Asymmetric encryption solves the key exchange problem during the TLS handshake. The browser and server use public key math to agree on a fresh symmetric session key. Then AES encrypts the actual page data at full speed. Asymmetric for setup, symmetric for bulk traffic. That hybrid design is why modern browsing is both secure and fast. But how does your browser know the public key really belongs to your bank and not an imposter? The server presents a digital certificate signed by a trusted certificate authority. Your browser checks the signature chain against a built-in list of root CAs. If the certificate is valid, unexpired, and matches the domain, the connection proceeds. If anything fails, you see a warning instead of a lock. Here is the detail most people miss. Modern TLS generates a unique session key for every connection. Even if someone records your encrypted traffic and later steals the server's long-term private key, they cannot decrypt past sessions. That property is called forward secrecy. Each visit to a site gets its own ephemeral key pair. Past conversations stay locked even if future keys leak. When you log into a site over HTTPS, your password travels inside the encrypted tunnel. The server never sees your password in plain text on the wire. Inside the tunnel, the server typically hashes your password and compares it to a stored hash, never the raw password itself. Encryption protects the journey. Hashing protects storage. Two different tools solving two different problems. From plain text to secure browsing, data scrambles with a key into ciphertext. Symmetric AES encrypts bulk traffic fast. Asymmetric keys solve the exchange problem. TLS handshakes agree on a session key. Certificates prove server identity. Forward secrecy protects past sessions. The lock icon represents all of this running before your page loads. If encrypted traffic now feels like deliberate engineering instead of invisible magic, that is System Sketch doing its job. Subscribe for weekly system breakdowns in plain English. Next time, we tap a payment card and follow the radio signal that never reveals your real card number. This is System Sketch.